Good evening, class. I am here recording this mini lesson for you guys. In case you have missed classes or you're just here to consolidate your understanding on some of the concepts, I'm going to be recording over the next week a few short recordings of on topics that we've either rushed through in class or that require a little bit more review or clarification for those who were not here. Starting with the solubility curves, I would like to start with this graph and show how we are going to solve some of the questions that follow on this worksheet. So we are looking at the solubility curves for different salts, and it doesn't necessarily have to be a salt, but any even organic molecule that dissolves in 100 grams of water. So really we are talking about solubility in 100 grams of water. Density of water being 1, 100 grams is equivalent to 100 milliliters. And we are looking at the solubility as it changes over a range of temperatures of the different salts. And you can see that every salt has a unique solubility curve. So its ability to dissolve in water, which is really the capacity of water to pull apart the ions in a salt like sodium chloride and surround it with the polar ends of water, which is the negative end, which is the oxygen, and positive end, which is the hydrogen on the water, surrounding it, allowing them to separate out the ions. So your positive hydrogen ions will surround the negative chloride ion, and your negative oxygen will surround the positive sodium ion, and this happens all around the ions. This ability to actually pull apart these ions and surround it with water molecules is the solubility of the salt. So I'm going to draw another water molecule here just to clarify that the positive ends of the water molecule face the negative ion, and the negative ends of the water molecule face the positive ion, pulling them apart or dissociating them. So what we are seeing here is really the ability of the salts to at different levels to dissolve in water. So you're looking at all these salts having their unique curves in order to dissolve in water. So some of them have a higher solubility than others, and others will be more soluble, mediocre solubility in water. So these are the different solubility curves at different temperatures. So basically what we are saying that in 100 grams of water, how much salt can you dissolve at a particular temperature? So using this graph, we are going to answer some of these questions here. I'll get you started with some of the easy ones here and leave some to your discretion, how you do it. But I'll just give you a quick guidance. So the first question here is asking us the solubility of sodium chloride at 75 degrees. So we're basically going to go to the sodium chloride, which is right here. Yeah, and we're going to look at its solubility at 75 degrees. So I'm going to really just plot on my graph a line that takes me across to approximately 40 grams. So 40 grams dissolving in 100 milliliters of water at 75 degrees. And you can see that sodium chloride doesn't actually change a lot over the range of temperature shown on this graph. So what you're going to say is 40 grams per 100 milliliters here is the solubility of sodium chloride at 75 degrees. Similarly, you would just be able to read which is the substance that's least soluble at 0 degrees. So you'd basically go at 0 degrees and find out which salt is least soluble. Then you would move on to the next question, which says which is the most soluble. Again, looking at the graph at 70 degrees and seeing which one is the most soluble, has the highest solubility. Moving to question 4, which substance experiences the greatest change? Here you're going to look at the highest slope. Which line or which graph has the highest slope on the for the different salts, and find that out. Question number 5 here is asking you if 47 grams of potassium nitrate is added to 100 milliliters of water at 30 degrees, is the resulting solution saturated or unsaturated? So you're looking at potassium nitrate, which is this graph here. Yeah. At what temperature was it again? At 30 degrees. So at 30 degrees, what was the solubility of potassium nitrate? It's about 47 grams here. Is it saturated, unsaturated, or supersaturated? So when you're looking at saturated salts, they will be on the line. On the line is your saturated amount of solute in the solvent. Above the line, above any of these graphs, you will have the supersaturated, and below the line you would have unsaturated. So if I take, let's say, let's take a good example here. If I take 120 grams of potassium nitrate at whatever this temperature is, this is unsaturated in 100 milliliters of water. I need to have more than that for it to be saturated, which would be about 145 maybe. So in this particular question over here, you would say that it is either saturated, supersaturated, or unsaturated, depending on where that 47 grams lies, whether it's on that line for sodium potassium nitrate or not. So you can judge that looking at the graph. The next question is asking you if 300 grams of potassium iodide is added to 100 milliliters of water at 40 degrees, what mass of the solid remains undissolved? So now I need to go to 40 degrees and look for potassium iodide at 40 degrees. What's the amount that I'm going to dissolve? So I'm going to go all the way to potassium iodide on this line and find out how much do I need to add to it. So what I'm seeing here is approximately 198 grams in 100 milliliters would give me a saturated solution. But if I have 300 grams that I am adding, the water is not going to be able to dissolve it, and it's going to spit it out in the solution or crystallize it and leave it as undissolved. So I'm going to say 300 minus the 198 that the water can dissolve is equal to the 102 grams of the solid, which is going to remain undissolved. Right? The next question is asking us what volume of water would have to be added to the solution in question 6 in order to dissolve the remaining solvent. So what I'm going to go with is, again, 198 grams dissolves in 100 grams of water, or you can say 100 milliliters of water, just to keep it a little bit different. So 102 grams will dissolve in how much? So then you can cross multiply, which is the trick that we're going to use all the time. So you're going to multiply that with that, and 198 with the, you can call it a X or a question mark. So 198, I'm going to leave it multiplied with the question mark, should be equal to 102. So it's cross multiply and equate. So with the 100, should be able to evaluate or calculate the value of the question mark, which is 102 multiplied by 100 divided by 198. If you have your calculator with you, you should be able to get, let's see how much that is. I am getting 51.5 grams. So if I add 51 grams of water is required to dissolve the rest of the salt in that particular solution. Question 8 is now looking at 50 milliliters, not 100 milliliters, but 50 milliliters of a saturated solution of potassium nitrate at 80 degrees. And if it was cooled to 20 degrees, what amount of solid or how much mass of solid would be crystallizing out of the solution? So I'm going to have to go back to the graph. Just double checking, this is potassium nitrate at 80 degrees. So we're going to go with, let's try and get a different color. Here we are. So at 80 degrees, potassium nitrate solution is giving me 170 grams. So if I require 170 grams in 100 milliliters to be saturated, how much do I need in 50? It's basically half of that, which is 85. So this is going to be 85 grams in 50 milliliters of water. At 80 degrees, this is both at 80 degrees. What do I have at 20 degrees? When I look at the graph again, at 20 degrees, potassium nitrate is showing me about 32 grams solubility in 100 mils. So 32 grams in 100 milliliters. So 16 grams in 50 milliliters at 20 degrees. So what's the amount that's going to be crystallizing is 85 minus the 16. That'll give me the answer. 85 grams minus the 16 will be the leftover salt, undissolved or crystallize out. So you can just fill that out. Whatever number you get there, you can just fill that in there, and that'll be your answer. Question number 9. What mass of water needs to be added to 100 grams of potassium iodide at 50 degrees to make it saturated? So I want to find out from that potassium iodide at 50 degrees. So let's try and get a different color pen. At 50 degrees, potassium, is it iodide, was it? Yeah, potassium iodide at 50 degrees. I'm going to go all the way up to the top here. At 50 degrees is about 215 grams. So if I want a saturated solution, I need to have 215 grams in 100 milliliters of water for saturated solution at 50 degrees. So I have only 100 grams. How much water would I add? In how much water? So again, I'm going to multiply this with this and this with the question mark and find out the question mark. Cross multiply and equate. 215 multiplied by the question mark is equal to 100 multiplied by 100, and therefore The question mark is equal to whatever your answer you get, 100 multiplied by 100 divided by 215, and whatever answer you get there. The last question here is very similar again. You got 6 grams in 60 milliliters of water. At what temperature would the solution be saturated? So really I can only compare in 100 milliliters. So really I want how much salt do I need to add if I had to have 100 milliliter amount of water, and that's going to be 60 multiplied by 100, 6 multiplied by 100, not 60, divided by 60 will give me the question mark, which is equal to 10. So 10 grams per 100 milliliters of water. So I'll go back to the graph and check. 10 grams at, not there, not 10 degrees. 10 grams would give me 20 degrees at 20 degrees. 10 grams in 100 milliliters. So it doesn't matter that I don't have the 10 grams. I'm using only 6 and 60. It's the same ratio. And therefore, my temperature is going to be 20 degrees. They're asking me at what temperature would this solution be saturated. It would be at 20 degrees. So that's my answer. All right, so that's the end of the solubility worksheet. What I want you to do is really get onto chapter 13, where you are looking at units of solute in solvent, which could be parts per million. Let's try yellow color. Parts per million, which is milligrams of a solute in 1 liter, or parts per billion, which is micrograms per liter. These are very small quantities in a liter of water, and they are usually used for heavy metals that you might find in water, or some kind of impurities or toxins that you find in water that might be present in very small quantities, but they need to be measured in those quantities to identify if they are safe or not. And then you could have, we talked about this one already when we did our titration. If you have mass of something in 100 grams of sample, or mass of something in 100 milliliters, so mass over mass or mass over volume. These considerations are also called percentage mass over mass or percentage mass over volume, because it's out of 100. So when you're considering your solute out of 100, it's going to be a percentage. It's equal to a percentage, either mass over volume or mass over mass. The other one that you have looked at is molarity, and we've learned this one as moles per liter. So this is the regular unit that we would be using for concentrations. Within that chapter, you will also see a concept of dilution. So if you're diluting something, you want a certain kind of substance to be diluted, like we did the acetic acid. We diluted it 10 times, meaning we took 10 milliliters and diluted it to 100. We can actually calculate the concentration of the new solution using this dilution formula. This is a really important formula. C1 V1 is equal to C2 V2, where C1 is equal to initial concentration of the original solution. V1 is the volume you take, volume of initial solution, and C2 is the final, the new concentration after dilution, and V2 is the final volume. So you might take 10 mils, as I said, and dilute it to 100. So 100 is your final volume. After dilution. So if you can do these calculations of initial or the final concentration or volume, out of the 4 parameters here, you should be able to calculate one missing one if you know the other 3. So these are important, and the important formulas that you have learned, which this is derived from, is N is equal to C times V. Okay, so concentration times volume in liters. Also, our original formula, N is equal to mass over molar mass. If we are going to shuffle between mass over volume and things like that, we should be able to shift between these formulas. Remember, this one is important because it's only used for dilution. C1V1 is equal to C2V2 is only used for dilution. Review chapter 13 and then come back to the next video, which I will record in the next day or 2. So this is for chapter 13. If you want to consolidate and be able to solve some of the problems, look at this one over here, like mass of volume, percentage volume over volume, meaning volume of a liquid in volume of another liquid. Yeah. So we'll do some practice questions on this one in my next short mini lesson. Meanwhile, if you have any other questions, please do not hesitate to get in touch.